Okay. So last we were talking about this concept of items and closure that we were going to need for LR parsing. Reminder that this entire slide deck, there will be no homework on it. It's not related to anything that will show up on the exam. You don't need to know it, but it is, I think, very enlightening for kind of how LL parsing works. And if LL parsing didn't work, then what could we do about it? How could we still get grammars that can be parsed more efficiently than CYK? So we talked about this concept of an item, which is a production with a marker symbol in it. We're using the dot for that. And the placement of that dot tells you what is currently on the stack and what needs to continue to be pushed onto the stack in order to replace a right-hand side with a left-hand side, which is what we do if we're trying to use bottom-up parsing. Rather than replacing left-hand sides with right-hand sides, we're replacing right-hand sides with left-hand sides. We then started talking about closure, which is what we need in order to move the marker in an item forward over a non-terminal. Because as we know, we're not pushing non-terminals onto the stack, we're only pushing terminals onto the stack, which means that we need to do a reduce operation to get a non-terminal on the stack so that we can map some right-hand side to a left-hand side and do another reduce. So if the marker is just to the left of a non-terminal, we need to first get that non-terminal on the stack so that we can move past it. So that we can eventually replace the right-hand side with this marker with the left-hand side and do that reduce operation. So we defined a closure as a set of elements. We start with a single element that is the current production with the current item, the current place of the marker. So we loop until no more items are added to the set. What do we do inside of this loop? We're going to go through every production in the set. So it starts out with a single element in it. We're going to look at this production A arrow W dot V, where the A is the left-hand side of the current production as defined up in the second point. And then W dot V is just W is everything to the left-hand side of the current marker in the right-hand side, and V is everything to the right-hand side of the marker. For each production, if a dot appears before a non-terminal, so basically if V starts with a non-terminal, then we need to add a new production to the set, V arrow dot right-hand side, for every possible right-hand side that we could have. If there are multiple productions, B arrow this, B arrow that, we would be adding each of those productions to this closure set. Does that make sense? So the definition of closure W dot V, we have A arrow W dot V, the current item. If V starts with a non-terminal, we're going to keep adding to this set. And then for each one of those that's added, we have to figure out if those start with a non-terminal and continue to add additional productions and additional productions to this set. Let's give you an example. Here's a context-free grammar. Let's calculate the closure of S arrow A dot SB. Go ahead and give this a very quick shot if the last slide made sense, and we'll go over the answer in something like a minute. First of all, is it clear what needs to be done? Looks like the answer might be no. Let's go over the example. So we start by adding this production. with this item into the set that is the closure. So the closure of S arrow A dot capital SB starts out being S arrow A dot capital SB. Great. Now we need to loop through every element of the set, which is just a single element now, and ask, is there a non-terminal directly to the right of the marker? In this case, the answer is yes. S is directly to the right of that. So we now need to add S arrow dot the right-hand side for every production that S can produce. So S arrow dot A capital SB and S arrow dot A. So now we have 3 elements in the set. For each of these elements, are there any new elements that we need to add to the set? Or are we done? Do any of these elements that we haven't looked at so far have a non-terminal to the right of the marker? Yes, the dot A, dot capital A. So now we need to look at every production where we have A arrow something and add that production with the marker on the left-hand side of the right-hand side. So that will add A arrow dot B capital A and A arrow dot C. If we iterate over all of these elements, we find that no new elements start with a non-terminal or have a non-terminal to the right of the marker. So we are done. We terminate. This is the full set of the closure of S arrow A dot SB. This tells us what is necessary to be able to move the marker past the S in this original thing. In order to get this, to move this from here to here, one of these has to be true. We have to be able to have said that we have found a C, which becomes an A. That A can then move past that A to create the A, and the S can be created from that A so that we could then move past the S. That's basically the purpose of this closure set, is it defines a sequence of operations that are necessary in order to advance the marker past a non-terminal in the closure, which helps us to get closer to being able to do a reduce operation on the right-hand side of the original closure. Because if the marker gets all the way over here, that tells us that all 3 of these elements are on the stack in this order, so we can reduce the right-hand side to the left-hand side. So to be able to do that, we need to know when elements are on the stack that can be reduced to an S. And again, that's what this closure is helping us to figure out, is when can we do that? This will go explain that idea in a little bit more detail. So there's a marker to the left of capital S in an item. To break this down into what it means intuitively, there's an A on the stack, and capital SB is not yet on the stack. We also know that a shift operation placed the A on the stack. To get the capital S on the stack, we have to reduce an S production, saying that we take a right-hand side where the left-hand side is capital S. So eventually we need stuff on the stack for some element of the closure of this production. If that is the case, then the right-hand side of that closure will reduce to S. And then we know that S is on the stack and we can move that marker past the S. Questions about that concept? Does that intuitively make sense? Kind of getting some blank stares. Do I have an example of this? Not quite. Let's see if I can generate an example on the fly. So I'm going to go back to our old grammar so that I see all the productions at once. And you can imagine that let's see, what is a reasonable string? We're going to have a reduction to this. If we write out S arrow A S B arrow, this S is going to become an yeah, we'll make that an A. And then this A can become a C. That's fine. All right, so there's a full derivation of a string that eventually reduces. If we're going to go from the right-hand side to the left-hand side, we do a reduce operation here, and then we would do a reduce operation here, and then we would be able to eventually do a reduce operation here for that. So immediately, when we see ABC, we're going to see this whole algorithm in a second, but we can shift the A onto the stack because let's draw stacks underneath here. We have an A on the stack because there's no rule that can possibly reduce a lowercase a into something by itself. So there's no branching that we need to consider at this point. We then shift the C on the stack. Now we have an option. We can choose to shift the B onto the stack, or we could choose to do a reduce on the C and replace it with a capital A, since this is the right-hand side of some left-hand side. The goal is to eventually not have this choice at all. So we can see if the goal is eventually to get to something that when we have this A on the stack, we have read it so far in this production. So this is what tells us that the A is on the stack, but the capital S and the lowercase b are not on the stack yet. So we would see the S arrow A dot SB as an element where the A is on the stack and the S and the B are not yet on the stack. So the question is what's being put on the stack possible? Can we generate an S with what's currently on the stack with A and C? And if we look at the actual closure of S arrow A dot SB, we see A arrow dot C, which tells us that we can use this production and just this production to eventually backtrack to be able to move this S forward one. And if we see what happens when we do this, we'll see that that is in fact possible. So we reduce the C to a capital A. We reduce the A to a capital S because we know since this is in there that we can produce an S from it. So we just follow, since it's an element of the closure, we can do exactly that. Which allows us to now, since the S is on the stack, this has been converted into S arrow A capital S dot B. We basically, with the concept of this closure, knew in advance we could do this process with some future steps. Does that help? Does that make more sense? Seeing how this as an element of the closure tells us that we can backtrack all the way to here to move this one forward. When we saw this on the stack, we identified it as this case in the closure, and we're able to backtrack and eventually move the marker forward one. And sure enough, the next element of the string is also going to be a B. So when we add that B, that can move forward and we can do a reduce. And since with LR parsing, we store the entire string's look ahead and not just a single character, we can actually see with multiple look aheads whether or not it is worth going through that reduce process or not. So when we do this, we can finally do one last reduce and just get S on the stack. And as we learned last time, once S is on the stack, we can transition in the NPDA version of this from state Q0 to state Q1, removing the S, which would just give us an empty stack, which we could then use for acceptance. This grammar can generate this string. Hopefully that helps it make more sense. How do we feel about that? Yeah. Question?
So, can the slides for this be posted at the end of class?
Yes, yeah, I can get these up as well. Just for future, for reference, even though they won't be on the exam or there won't be any homework for them, but yeah, I can upload them for your perusal. In fact, they might already be up.
I can check.
I feel like, I think I remember putting all of them up saying, why not at this point?
Oh, yeah, they are.
Sweet. Are there any questions that can help make this process make more sense? Or what do people not understand or not? It's not really the best question to ask usually, but if someone could elaborate on their either understanding or confusion, that would help me to understand where you are.
Yes, like I'm still just like struggling with like the marker terminology, because like. you said
Yeah,
Everything on the left side is on the stack, right?
yeah,
So then why is it that in the example, we push like the C onto the stack? And we're using the A to dot C, wouldn't dot C mean it's not on the stack?
okay, that is a good point. It's basically saying that if we see a C here, we can replace it with an A, which we could then replace with an S, which we could then use to move forward here. It's kind of if we're in this position and we see this, this is what allows us to, if we can complete the closure of this, then it allows us to complete the closure of something that backtracks to that. So we have to complete the closure of one of these elements in order to be able to backtrack. So if we can map that to the string, so we see that the next thing that we're going to put on the stack at this point is a C, that tells us that we complete the closure of this, so we can backtrack to this, so we can backtrack to this and move it forward.
Okay.
Excellent point. Excellent point. Yeah, we have to be able to complete the closure of this in order for this to be reduced to an A. So we wouldn't just be able to see a B and then immediately be able to do it. We'd have to have B capital AC. And then if we had that on the stack, then we could backtrack. Yeah, we have to complete the closure of one of these elements to complete the closure of that. Does that help? Closure is tough. Other questions about this? I feel like this is probably one of the harder things of LR parsing. Yeah,
So if you were to put this into an algorithm, like actually code this out,
yeah,
are you kind of like beforehand calculating closure on all of the productions, or is it something you're doing as you're parsing through?
yeah, you're actually calculating where the closure of each one of these or the elements of what's currently on the stack, and you're keeping track of all of these in parallel.
Oh,
And that tells you when you have the option to do a reduce, so that you can do a check to see, should I shift or should I reduce? Like, if I reduce, will I be able to make progress?
Oh.
And that will end up being a subroutine of the actual algorithm. That's another really good question. Anything else? Even general confusions, I don't understand something, perfectly valid. Getting my racer. Yeah. All right, so here was our example. Does exactly the same thing or close to the same thing. Just in words, this allows us to move the marker forwards once we're able to do that. If we resolve that closure, then we can move the marker one character forward in the closure of that item. How this is actually going to happen in practice? So we're going to use a DFA. Our old friend DFA comes back and we can make a DFA for this entire process. So that rather than actually having to go through a full subroutine and calculate something, it's already embedded in a state machine. And the transitions of that state machine become possible when you have certain elements of certain closures. So we're going to make a DFA for it. With everything that we've talked about so far, we would be able to complete this, but we need to be able to look down more elements of the stack to determine if everything is on the stack. So great, but not great. The DFA is going to help us to be able to determine this. If we end up in a final state in the DFA, it tells us that there is some reduce operation that we can do. And that reduce operation will be defined as part of the state of the DFA. So every state in the DFA is going to be associated with some set of items in the grammar. Remember that an item is just the right-hand side of a production with a marker in it somewhere. So there's going to be some set of items that will be associated with a particular state. That tells you if you're in this state, then here is what is on the stack associated with this particular production. As we parse the string, we trace through the DFA. If you're in a final state, then there is some right-hand side that is on top of the stack, so a reduce is possible. If we're not in a final state, that means we can only choose to shift from here. We cannot choose to reduce. So here's the full algorithm to build a DFA from LR parsing. We're going to go through this process as an exact example here momentarily. So we are going to take as input a context-free grammar. We're going to create a new grammar that is going to basically be the same grammar, but with every possible production being every item from the past one. We're also going to make sure that we make a new start state, S prime. We're also going to use a Q object to determine where we have and haven't been with regards to the DFA. We want to, for each state, we want to figure out what are all of the transitions out of that state. Every new state that we make will just be added to this queue to figure out the transitions out of that state. And eventually we'll terminate this process with a full DFA. So we want to compute the closure of this new starting state S prime, arrow dot S. This is how we begin everything. Basically, we're saying that in this state, we have not yet been able to parse the starting state. And if we can backtrack all the way to that point, then we can move the dot S one space forward to S dot, which tells us that we have successfully parsed a string in the grammar that can be derived from the starting state. So we have a queue we're going to call states. We put this state 0, that is the dot S, into the queue. We're going to randomly take an item out of the queue. We're going to dequeue an item, and we're going to parse that for every item in that state with a non-terminal in the next position, we're going to create new sets of states. Then we're going to add those in. I'll actually come back to this, I think, after the example, because it will make much more sense than just going through the actual algorithm. If you have an example in your head as you do that, that will make more sense. So the question that you might see for something like this, again, not on the exam, not on the homework, but it's if you encounter this, then it's an LR parsing DFA construction question. So here's a grammar, the same grammar we've been working with. We're going to, step one, add the new start symbol, S prime, and the new production to the grammar, S prime arrow S. We're going to number all of the productions in the grammar with this new production as element 0. We'll make a start state Q0. We're just gonna, from now on, instead of calling it Q0, we're just gonna, this is state 0. State 0 represents production 0 in the grammar. We need to calculate the closure of that. So S prime arrow, I guess that should be a dot S. Yeah, that's bad. S prime arrow dot S is going to include the element S prime arrow dot S. Since dot S is a non-terminal on the right-hand side of the marker, we need to look at all productions that start that have the left-hand side of S. We will add both of those into this with the marker at the very left-hand side of that. That's the next two elements of that. S arrow dot A capital SB, S arrow dot capital A. Since one of those has a right-hand side of the marker that is a non-terminal, we add every A arrow production with the marker on the left-hand side or the right-hand side of the production. That gives us the closure of S prime arrow dot S. We associate this entire set of closure with state 0. So you can now imagine a DFA as an object where we have a state and a closure. So we have a tuple that's a state and a closure. So it looks something like this. We have the state, and then below it, we have a box that contains the set of every element of that closure. We then add each one of these productions to the queue. Each one of these is going to define something, some kind of transition out of this state 0. So we can start by, basically we want to move the marker for each one of these over 1, and that represents the transition out of that state. If we can move any one of these over 1, represents a transition out of the state. So to move this past S, it creates the closure of S dot, which adds nothing new. So there will be a new state, state 1, that is a transition out of this. For the next one, we want to move the marker over the A to create the new item S arrow A dot SB that would happen if we did a shift with an A. We then calculate the closure of S arrow. I think that should say A dot SB, not dot ASB. So A dot SB, S arrow dot A arrow dot B capital A, etc. You create state 2 and associate that with this. Continue the process for the remaining states that are out of state Q0, and you end up with this. This is just the first step of this process, because now we have added Q1 or state 1, 2, 3, 4, and 5, all to your list, your queue that we called states. And now we have to go through each one of them and figure out what do their transitions lead to as we go over one element of that and calculate the closure as you move the marker one space to the right. Does it make sense how we did this associated transition? What each of these transitions mean? We basically say if we are able to reduce to an S here, then we're able to move past this. So we see an S, we're able to pop an S, we're able to basically go here. If we shift an A onto the stack, we're able to go here. If we reduce to a capital A, we're able to go here. If we shift a C, we're able to go here. So we need to add to a queue all of the states to expand, which are all of them, except for the ones that don't have any new elements associated with them. So 2 and 4 didn't have anything new. Sorry, 1, 3, and 5 don't have it. They have a single element that's not, the markers at the far right-hand side. That's why we don't need to expand them. For 2 and 4, there are elements that need to be expanded. So we need to figure out what happens when we move the marker one space to the left of each of those, creating additional transitions. But note that when we calculate some of this set, it's going to map to an existing set from an existing state. So that's how you get arrows to existing states. We'll see what that looks like momentarily. So we only need to expand states 2 and 4. We can expand state 2, creating 5 new states, but some of them have the exact same set of elements as existing states. So instead of making a new state for that, they will have a transition that leads to an existing state. We continue this entire process until there are no more unvisited states. This leads us to the final DFA that looks like this. It's a little bit intense. But we can see all states where the marker is on the far right-hand side ends up being a final state. That tells us that we can reduce because we've reached the end of some kind of production. Like for instance, when we're at the end of C dot here, we say that we can reduce this to an A. As we reduce this to an A, we get to move this past this A back here. So we can, by seeing this as a graph that we can traverse, we can now use this as a lookup table in the LR parsing. So this DFA is going to be part of the LR parsing algorithm to be able to calculate this efficiently. When I said this was harder than LL parsing, I meant it. This is a little bit more involved. I would not actually want you to go program this as part of a project that you only had a week for. For a long project, maybe. But this now defines all of the associated items and closure for the entire grammar and how you can go through this entire process. What you can add to the stack, what this allows you to do. When you reduce, you actually go backwards in the DFA. So you move forward with shifts or with figuring out elements, and then you go backwards when you do a reduce. The idea is that you eventually backtrack to Q0 with nothing left in the string, where you can move to this state and finally accept the whole thing. So with all of this in our toolbox, we're finally ready to talk about the actual full LR1 parsing algorithm. So the prior algorithm just helped us to build this DFA. This DFA doesn't fully solve LR1 parsing, but it's the final thing that we need to be able to implement LR1 parsing. So now given a query string, we start at the start state of the DFA. We're going to repeatedly apply shift and reduce operations until we have just the start symbol on the stack. A shift moves us forwards in the DFA, so we're going to follow an arrow from one state to another state, eating the associated character of the shift. So current symbol in the input string, follow the transition on that symbol from the current state in the DFA, pushing that symbol onto the stack. And transitioning the associated state. When we reduce, rather than moving forwards in the DFA, we're going to move backwards in the DFA for every symbol in its right-hand side, which may mean that it's multiple backwards transitions. Then at the end of that whole process, you must move forward to a state for the new non-terminal that was created as the part of that reduce. So as an example, let's say we do, A capital S B. So we would shift the A. We see the capital S, and maybe the capital S comes from a C. So this dot C here, we can follow the C to this Q5. This Q5 tells us that we can reduce with this C dot. So this tells us, pop the C, because it's stored right here in the item, pop the C, push the A that is the left-hand side of this. And now we go here. Now we see that we're at the right-hand side of this, which tells us that we can reduce. So we go backwards past the A transition, backwards through this A transition, storing this S that tells us we can now move here. Once we have the S, we know we've moved past the S in this A capital S B, and if we read the B, then we know that we're at the very end of this and can replace this with an S. So we backtrack through B capital S A, B capital S A, and push the S that tells us that we are now in the final state that tells us we can accept. So this DFA just stores all of the logic that I drew with all of the stacks in the prior example. It stores it all within the transitions of this state machine. So if you store a graph representation of this object, you are capable of doing any amount of parsing that you might care about. So this just tells us in words everything that I just showed on the board. Basically, you're going to be doing some number of backtracks. You store on the stack the state number that you visited to do this. So you're actually going to store a tuple, the letter on the stack and the state number that you were in. And that helps you, once you start popping things, to backtrack to the associated states that it tells you to go to. Let's see the full example. I like to think of this as a tuple rather than a state followed by or a character followed by a state number. I don't really love that. I would prefer these to be tuples. A2, A2, B4, C5. So our single character look ahead, since it's an LR1, we're only using a single look ahead character. When we're in state 0, the look ahead is an A. So we shift the A onto the stack, which tells us that we move to state 2 in the DFA. So as we shift the A, we move to state 2. So we want to store A2 on the stack. We then see a B in our string. So we're going to shift the B because we cannot reduce. We're not in a final state in the DFA. So we add B, the character that we're shifting, and the state that we transition to on that, which is state 4. So we add the tuple B4 to the stack. We add the C with a shift. So C tells us to transition to state 5 in the DFA. That goes on the stack. Now we can choose to reduce. So we take the C5, and this tells us now that we can backtrack to A, and then we move forward from the A to get to state 7. So this information, this state 5, seeing and peeking at this state 4, allows us to see where we go, And then follow from there, the transition out of that state, reading the capital A, that gets us to state 7. Then we do a shift. Then we do a reduce, and we see that all of this information, as you pop it off, tells you where to go to backtrack. If we did a peek to the stack, it tells us to go backwards from state 9 to state 7, state 7 to state 4, state 4 to state 2, and then the transition out of state 2 will be to state 3 when you read this A. So all of the information that you need for this is actually embedded in the stack. And you can imagine this visually as we transition across the DFA as well. All of this will map. We can do another reduce with the A and the 3. We go backwards to state 2 and then forwards through S to state 6. Then we do one more shift, B8. Then we're able to reduce the ASB. We go from state 8 to state 6 to state 4 to state 0, and from state 0 to state 1, which tells us that we can accept because we've moved past the S and we're also at the end of the string. The look ahead is the $sign. So between the empty stack, the final state here, as we get rid of the S here, we end up with a bottom of stack character and a string character that tells us we can accept. To help with this, I included some words from the textbook as well. That just goes through the exact language that we did. And now I also on the next slide have this as something that we can do here. You can actually map the exact process that we went through in the stack on this slide. So maybe we go through this visual example. What's nice is each final state, in this case, only had one reduce. That tells us that this grammar is LR1. A grammar that is not LR1 might have a final state with a transition out of it to a non-final state. It says that here we could reduce or we could transition to a non-final state and shift. Maybe it is a final state where you could shift to the point where you could reduce from there as well. But that would be an example of what is something that is not LR1, is when you have the ambiguity of when you could shift or reduce in this DFA. In which case you would need to use a larger look ahead than a single character to be able to figure that out. With the last few minutes, I think I'll just be able to try to tie this diagram to the DFA. So in state 0, we're going to shift the A on. If we look at the DFA, shifting an A from here tells us that we move from state 0 to state 2. That shifts the A. We also see all of the closures associated with state Q2. We shifted a B from here, which went from Q2 to Q4. So we went A, B. So now we have A and B on the stack. So we can now shift the C, which tells us we go to state 5. If we're in 4 and we see a lowercase a, so it starts lowercase c, then we move to state 5. The only thing we can do from here is reduce. There's no transition out of this state. So we backtrack from 5 to 4. And remember that we stored this in the stack. So we pop the C5, we peek at the B4 and see the 4, and that tells us where to backtrack to. So it tells us to go backwards from state 5 to state 4. We moved past the C here, which allows us to move forwards in the A here. So we're going to transition out of this, reading the A, to this point, which tells us that we have B and capital A on the stack, and we've yet to see A on the stack. A transition out of this will allow us to reduce the whole thing. So we have B and capital A on the stack. The next thing we see is that lowercase a, which tells us that we can transition from state Q7 to state Q9. The only thing we can do from here is reduce, going backwards, lowercase a, capital A, lowercase b, and pushing a capital A. So we see exactly that. As we reduce from here, we go backwards from state 9 to state 7 to state 4 to state 2. So this tells us that we're gonna go from 9 backwards to the A, backwards to the capital A, backwards to the lowercase b to state Q2, and then push the capital A, which goes back to Q3. Which is what we see right here, state 3, capital A, that gets pushed. We can then reduce that, because if we look at the DFA, that's a final state. So we're able to move past the A, so we go backwards through the A to the S. That gets us to Q6. So we see here, S and 6 have been pushed. We then, from there, see the last B in the string, so we shift from Q6 to Q8 on the B. We're past everything here, all we can do is reduce. So we're gonna go backwards through the B, capital S and A, and then push an S, backwards through the B, the capital S, the A, and push an S. Gets us to state Q1, which is our acceptance state. It's not necessarily just a final state, it's the really final state that tells us that we have successfully mapped the string to the grammar. Now note that the final thing you have to check is that we're actually at the end of the string. So we need to see this look ahead character be the $sign in order to be able to accept that. That says that we've parsed the entire string. Questions on this process? So the important things from this slide deck were the DFA construction, and then the logic for how to actually parse it with a particular string. And that gives you an LR1 parsing algorithm. These are all of the slides that I have made for this class, and I feel like it's actually a pretty good stopping point. I don't want to dive too deeply into what would come next because it would just get more and more complicated. But my goal with showing you this is that compilers are actually a good bit more complicated than you might first assume that they are. This is just the parsing step. Remember that there were 5 or 6 steps to the compilation process, and this is just zooming in on one such process to come up with an efficient way to parse them. My plan for the next couple of days is just to let people focus on the study guide or the project or something that is useful to you. So I will be here as well to help you through anything that you are stuck on or would like questions about. So if that would be useful to you, that is what the next couple of days will be for. We'll have our official review session on Monday after everybody is fully studied and kind of a last minute, any questions before we take the final exam. I will also at that point have made the final exam so I can actually answer questions about that. But that is the plan for the last few days of class. I will see you tomorrow.